even though people are still kind of filtering it in, it looks like, but we're basically time to get started. Um, I don't know, maybe just a little chit chat in the beginning because it looks like we have about a half of everybody so far. Um, what we're doing, I guess, kind of outline the plan for the rest of this semester now until everybody gets on board. We have finished with our stress transformation and our strain transformation. Those were two pretty meaty, big subjects. And I'm certainly open to if anybody has questions on those. But what we're going to transition to is kind of a little bit of a preview to what you're going to be taking in your structural analysis class and or your material classes after that. So we're going to finish up by looking at deflection of beams today. We're going to rehash some of the equations that we found. If you remember, we went through quite a bit of theory to get to the flexural formula, which is sigma, the stress is equal to minus my over I. We're going to rehash that a little bit so that we can formulate how to find the deflection of beams by a method known as the double integral method. That's going to be today. And then we only have 2 more lectures after today. So the last 2 lectures are going to be finding deflections in beams and trusses using the energy method, or a method known as virtual work. And then the very last class is going to be a class in buckling for compression members that might tend to buckle. And will we be doing a final exam review next week? Yeah, I'm sure we will. There's going to be time, probably, if not a little bit after the virtual work, certainly there'll be some time after the buckling to go over the final exam. However, today's Wednesday, and then we have Monday, Wednesday of next week, and then we have our final exam on May 13th, I think it is. So just suffice it to say for now that the final exam is comprehensive for the whole 15 weeks that we've done this, but it's going to have most of its emphasis on the material that we have learned since we took the midterm. If you remember, the midterm carried us up and through chapter 6.4. So chapter 6.4 was really just the flexural formula, sigma equal to minus my over I. Since then, we have done biaxial bending, where you bend about the x and the y axis, and we've done combined loading, where we have axial load, moments about x or y axis, and then we did thin shell pressure vessels, and then we had a whole big segment on stress transformation, strain transformation, and then we have the last few lectures here. So that kind of gives you some idea of where to put your emphasis for the final. When I say that the final is comprehensive, sorry, I'm kind of doing 3 things here at once. When I say the final is comprehensive, it will have stuff like, in order to apply something that you need the moment, you need to be able to get the moment diagram. And that was kind of covered on midterm too. Or in order to find a deformation of an axially loaded member, you have to really know how to find your reactions, and you need to know that your normal stress is P over A, things like that. So you kind of have to master the earlier subjects in order to be competent in the latter subjects. That makes sense? Yeah, I'll still have office hours during finals week. Yes. Yeah, that's fine. And then, yes, you see my pattern, how I write my exams now. They will follow exactly the same pattern as exam 1 and 2, except that there'll be an extra question because you'll have 2 hours instead of an hour and 15 minutes. So there'll be four problems, maybe a few fill in the blanks after that. We'll see. And also, thank you for bringing that up, Ryan. Most importantly, we still have a few weeks before the final. If you had any issues with this Respondus lockdown browser type, please resolve those issues in the next couple weeks. I have no choice. I have to give the final exactly the same way I did midterm 2. So it's going to be the same format, the same browser that you have to download. Everything's going to be the same. I'm basically going to have the same rules about one page of notes, and you scan your notes and your work that you've done during the test. You scan those up to me. Basically, expect the same thing that you saw for midterm 2 for the final. Okay, so we've got, I think, most of who's going to join us is here tonight. Do I have any questions that I can answer for the final before we start the lecture?
Will we be able to use the cheat sheets we did for exam 1 and 2?
If you, I mean, you get one page of notes.
Oh, okay. So
So,
okay. Condense.
yeah, yeah,
Okay.
yeah.
That's fine.
Can the note sheet for the final be 2 sides? You don't want to write on that other side. That other side's ugly. That's just going to be ugly and discouraging. You want to keep it to one side, but I don't really care. If you want to write on the back side, the ugly side, then you can do so. Okay, tonight's lecture is the deflection of beams, and we're going to get started now. Let me get my little dealy bobber here. Okay, so in order to determine beam deflection, the first thing I want to say before we get into the nuts and bolts of how you actually get the equations for beam deflection, let's first talk about how it helps to sketch the deflected shape beforehand. It helps to use a little intuition before you try to apply the equations. So sometimes, a lot of times, until you kind of get the hang of these things, it helps to draw the moment diagram first. The moment diagram, now that you've gone through the graphic method, you can get pretty close to the moment diagram pretty quickly. It doesn't have to be perfect, but if you sketch the moment diagram first, then follow these guidelines to sketching your deflections. If you have a positive moment, then that means the deflected beam is going to be concave up, or it's going to take on a smiley shape. Likewise, if you have a negative moment, then you're going to be concave down, or it's going to be, and I know this isn't a real word, but it's going to be a frowny shape. If you have a pin support or a roller support for that matter, at that point, you can have no vertical movement, but the beam may have slope. So a pin or roller support does not prevent the beam from having a slant to it or a slope to it, but it won't allow vertical movement. A fixed support does not allow vertical movement or any kind of a slope. So it is fixed in both conditions. And so here's some examples. Simply supported beam, linear load on it. You can pretty quickly derive that the moment diagram is this parabolic shape. It has to start at 0, it has to end at 0. And if you have mastered the rules of the graphical method to drawing shear moment diagrams, then you'll recognize that this is a uniform load. So the shear has to be linear, so the moment has to be parabolic. The point, though, is that this moment diagram is positive. The whole span is a positive moment. So that means that the beam deflection is going to be concave up or a smiley face, which is, you can also intuitively just see that a simply supported beam with load pushing down on it is going to push the beam down into this smiley shape. So far, so good? Okay, so a positive moment, smiley shape. Now we can look at a beam that has a negative moment on it. This is a load pulling straight up on the beam, which is the opposite of what we're used to seeing. But this is pulling straight up, and so the reactions are pulling down. The point load causes a uniform shear, which causes a linear moment. So the moment diagram is like so. And this is a negative moment on the whole span. So the deflected shape is going to be a frowny shape. And again, some of these are just intuitive. You can just picture in your mind, you pull straight up on a stick, it's going to bend up like that. Okay, here I've got a fixed cantilever. So a point load on the end of a cantilever produces negative moment over the whole span. And we have our characteristic frowny shape. So there's your negative moment. There's your half frowny. However, notice though that at the fixed point, you have zero deflection. You have maximum deflection out here where the load is, but you have zero deflection at the fixed point. You also have zero slope at the fixed point. It's a little hard to see in this diagram, but this perpendicular line is absolutely up and down. So the axis of the beam is horizontal right there at the support. Here we have a simply supported beam with a cantilever, uniform load. The uniform load tells you that the moment diagram is going to be parabolic. We've done a few of these when we studied how to do the graphic method. And you don't really, for these purposes, you don't really need to nail down exactly where that inflection point is right there. But suffice it to say that I have positive and negative, don't I? So in the positive moment region, the beam is going to be deflected in a smiley shape. In the negative moment region, the beam is then going to take on a frowny shape. And the inflection area is right in here someplace. So that's your transition from smiley to frowny. Any questions so far? Okay. So here we're going to redo a little bit of what we talked about before when we derived the flexural formula. We're going to start with the beam before bending, where the neutral axis is, of course, horizontal in the same plane as the beam itself. Once the beam is bending, then the neutral axis, of course, has to bend with the beam. And we did this before, but what we're looking at is with no load, then the fibers at the top of the beam will have the same length as the fibers at the neutral axis. So delta X is going to equal delta S at the neutral axis. But once you put some load on it, then the top fibers are going to shorten. The bottom fibers are going to elongate due to tension, but the top fibers are going to shorten. So delta S is going to shorten to delta S prime at the top here. So remember our equation for strain, epsilon, is equal to the new length minus the original length over the original length. So delta S prime over delta S divided by delta S. But the original length is the same as the neutral axis length. Neutral axis length doesn't change because it's at the neutral axis. So we can say delta S prime minus delta X over delta X is the strain. And by small angle theory, we can say that the radius times the change in angle here. So as the beam bends, this produces an angle. So actually I labeled that theta, but I labeled it delta theta down here. So it's really kind of the change in the angle due to the loading. So by small angle theory, delta x is equal to sine delta theta times rho, which is delta theta times rho. And by the same token, if I reduce the radius from rho to rho minus y, then I have delta s up here is equal to, or actually delta s prime is equal to rho minus y, this radius, times delta theta. So you see how we're getting the relationship here. We're relating delta x to rho and delta s prime to rho minus y. So y is the distance from the neutral axis to the point of interest. And so my strain, epsilon s, is equal to, now all I did is I just took delta s and plugged that in here, and delta x and plugged that in there. So I get this equation here. The rho's all drop out. The delta thetas all drop out. Or I'm sorry, not all the rho's drop out. And what I'm end up with is minus y over rho. And this was a proportionality. This is when we're deriving the flexural formula. So I have epsilon is a proportion of epsilon max. And then I substituted epsilon for sigma over E is equal to minus y sigma max over CE. Again, kind of rehashing this, but what we're getting towards, sigma is equal to minus E over y rho. Then we found the location of neutral axis. We sum the integrals of these little pieces of the forces to equal each other. And we plug and chugged until we got to something that made some sense. And neutral axis located at centroidal for cross section. Summing all stress about neutral axis, the moment is equal to the sum of the moments area ydf. I'm kind of skipping a little here because we covered this. And there was our final solution right here. Sigma is equal to minus my over I. So that was our flexural equation. This is the second time I presented this exact same material, so I went through it certainly much faster this time. Do I have any questions before I move on to the new material? Okay. So the new material. We know that sigma is equal to minus my over I, and epsilon is equal to sigma over E, that's Hooke's law, so that epsilon is equal to minus my over EI. And from before, we found that epsilon is minus y over rho. So I can rearrange this to say that 1 over rho is minus epsilon over y. Substituting back in. Minus epsilon over y is equal to my over ei divided by y, which is m over ei. So this is an important finding right here. This finding is that 1 over rho, which is the radius of the curvature, 1 over rho is equal to m over ei. The moment divided by basically the stiffness of the beam is what ei represents. Remember, E is Young's modulus, so that's the stiffness of the material. I is the second moment of the section. So I represents the stiffness of the section properties, E represents the stiffness of the material properties. Combine the two together, M over EI is known as the curvature of the beam. So if we define the beam deflection as little v, this is not shear, this is little v, and little v as a function of position on the span x, then at some arbitrary point x, we can solve for the deflection v. V is equal to a function of x. From calculus, we get the solution to okay, so what I've done here, the solution to v is equal f of x, 1 over rho is equal to m over ei. Yeah, this is a quantum leap right here. They don't really tell you how you get this, but it's part of a partial differential equation. And when you solve it, you get this, quite frankly, kind of monstrosity. So it was basically a leap of faith from here. You had to differentiate this with respect to x to get the v. Anyway, this is your final. So the curvature is equal to this expression. So this whole expression is equal to m over ei, which is pretty nasty looking, right? Fortunately, dv dx is the slope, and the slope is very small. So what you might see sometime later in your career is you'll see that frame programs or ETABS or SAP 2000 or programs like that will differentiate between small deflection and large deflection. And most of the time when you solve for deflections using this software, what you're solving for is small deflection. Small deflection is like a few inches on a beam that's 20, 30 feet long. That's small deflection. So a deflection of a few inches on a beam that's several feet long, this slope right here is a very small number, almost equal to 0. And so what we can do with that small deflection assumption is we can take this out of the equation. If this is 0, 0 squared is 0, 1 plus 0 is 1, 1 to the 3 halves is still 1. So this reduces to a much more palatable d squared v over dx squared. If the software says that it's doing large deflection, which is a pretty sophisticated piece of software now, then what they're saying is that they're not ignoring this point right here, which greatly complicates the expressions. We are going to ignore it. We're going to consider small deflection behavior and move forward with this formulation right here. So therefore, if I take the EI over on the other side, then EI d squared v dx squared is equal to moment as a function of x. This is known as the double integral method for beam deflection. And where do I get the moment as a function of x? Anybody seen that before? Anybody from the moment graph? Anybody remember before we did the graphic method of finding shear and moment diagrams? Before we did that, we had to solve for the moments as equations. Yes, so I had asked you, I need the equation for the moment from 0 to 6 feet or 6 feet to 18 feet. That's what this is. Those were equations for the moment as a function of x. That's what this is, the equation for the moment as a function of x. If I differentiate this expression, then I have EI d cubed V over dx cubed is equal to the function of shear as a function of x. And then EI d to the fourth V dx to the fourth is equal to the load as a function of x. Because remember, all of these expressions are linked together as the differential of one, the integral of another. Okay, are we ready for an example? See how this all plays out? Okay, so let's start with, we're gonna start with a pretty simple one here. Simply supported, it's a beam with a load P on it. The beam is L long and the load is applied at midspan. You'll see that these examples I'm about to give you, I got, I don't know, 3 or 4 of them. I don't use any numbers. I'm not using actual spans. I'm not using actual loads. What I'm going to show you is how the tables are created. If you look in your book or you look in any other book that has structural analysis in it, you'll see a list of tables that list common loading conditions like this right here. And they will label that table in terms of P, L, L over 2, and they will give you maximum deflection based on these variables. So that's what we're going to do. We're going to derive how those tables came up with those expressions. And then, of course, once you have the expression, you can always just go back to the table and plug in the actual values. If this is 10 kips and this is 30 feet, you can always go back to the tables and plug those in. So we're going to follow some basic steps here. You might recognize these. We must first create a free body diagram. We must find our reactions. So I'm going to sum my moments about A. I have, again, everything's in P and L, but P times L over 2 minus RBY times L is equal to 0. So RBY is equal to P over 2, as you would expect. Summing forces in the Y, RA is equal to P over 2. Now, if I decide on my cut points, remember all this? How many cut points do I need to completely describe this beam? 1? Well, just 1. No, I need 2, but for what I'm going to do here, 1 is actually going to suffice. You'll see how that works. Okay, so I have a free body diagram for cut number 1. And so remember all this. This is my end reaction. I have some arbitrary cut at X from the end. Positive moment, positive shear. Find shear and moment. My shear is equal to P over 2. Sum the moments about your cut point, and your moment is equal to Px over 2. Here is my equation for the moment from 0 to L over 2. And so back to my equation for dV dx over EI is equal to the integral of mx, which is equal to the integral of Px over 2, which is, if I take Px over 2 and integrate it, I get Px squared over 4 plus my constant of integration. So this was dV dx. To get to VEI, I have to integrate all over once again. That's why it's called a double integral. I have to integrate it twice. So now I integrate the findings from the first integration, go into the second integration. And I integrate again. So Px squared over 4 becomes Px cubed over 12. C1 becomes C1x, and I have to have C2. So I have 2 constants of integration. I need to solve those constants of integration using boundary conditions. So what do I know about this beam? The load was at midspan, So I know that dV dx, which is the slope of the beam has to be equal to 0 at the midspan. So therefore, at x equals L over 2, then dV dx has to equal 0. 0 slope at the midspan due to symmetry. So this doesn't always work, but it works when that load is right at the midspan. So that means that my equation here, all I do is I take this equation and I plug in L over 2 for x, and I plug in 0 for dV dx, and I solve for C1. C1 is going to equal minus PL squared over 16. Now I go to my second equation. I now know what C1 is equal to. So I can plug that in here. Px cubed over 12 minus PL squared over 16x plus C2. I need another boundary condition. So what do I know? I know that the deflection equals 0 at x equals 0 because I have to have 0 deflection at my supports. So now I can plug in x equal to 0 into here, and the whole thing is equal to 0, and solve for C2. So I plug in 0 for x, I plug in 0 for v, I solve for C2. C2 is equal to 0. Therefore, my deflection times EI is equal to px cubed over 12 plus PL squared over 16 times x. And I can simplify that to the deflection is equal to 1 over EI px cubed over 12 plus minus PL squared over 16x. So this is the general equation. This works anywhere. This general equation for deflection is valid anywhere on the span. Now you may be asking, or you should be asking, why did I only need one cut? Doesn't that violate everything I ever told you? Only one cut. And Nick there in the chat said two. Nick is right. I do need two. This is a very special case. It's a very special case because the load was exactly at midspan. So whatever the equation was going from the left to the midspan, it is symmetrical so that the other side is an exact copy of the first half. That's the only reason why. Otherwise, you would in fact need two equations for the moment so that you can get both parts of it. So does that make sense to everybody? Or do I need to expound on that?
Expound on that, please.
No problemo. Let me go back up a slide. Okay, let me go back up 20 slides. Whoa, there we go. This is a special problem. P is located exactly in the midspan. So whatever this beam does deflection-wise, and I can kind of sketch that in there hopefully, this beam is going to deflect like this. And I did my best, but whatever's happening on the right-hand side is an exact mirror copy of whatever's happening on the left-hand side, only because this is exactly symmetrical. That's the only reason. If this thing is just a hair off on either side, then that blows the whole thing. It doesn't apply anymore. But because it is in fact symmetrical, that means I came down here and I did one cut point. If I had done two cut points, I wouldn't have gotten any more information because everything I solve for and find out between 0 and L over 2, everything on the other side is a mirror image. So I don't need to solve for the other side. I already know it as a mirror image. So that's why I only did one cut. So then I got all the way down here and I got this but too far, general equation that is valid anywhere on the span. only because of that symmetry. Does that help?
Yeah, thank you.
Okay. Anybody else? Any other questions before we keep moving?
So does that general equation hold even if the beam and its p's aren't symmetrical?
No. And that's
Okay.
a
Okay.
great question. Thank you for asking that. No, it does not hold if P is not symmetrical. And the reason that it doesn't hold is right here. When you solve for your moment, this Px over 2 only holds if that load is absolutely symmetrical. Even though there's no L over 2 in here, but if that P was off to one side or the other, this reaction would not be P over 2 anymore. So if this is not P over 2, this is not Px over 2, and it blows the whole thing. So everything we did from here to here is invalidated if that load is not right at the midspan. Does that answer your question, Nick?
Yes, it does. I have one more question too. Can you re-explain how you got from dv over dx ei is equal to the integral of mx? Like I'm not sure, because you said that the equation below it, vei, is also that's equal to the integral of the
Yes.
moment.
Yes.
Oh, okay, I got it now.
You got it? No, you just said it perfectly.
Yes, I got it. Because I wasn't sure how you made the jump from dv dx to vi to vei, but yeah, now I got it.
Now you got it. Yes. For anybody else, what Nick said was absolutely spot on. The deflection is equal to the integral of the equation for the moment. That's why it's called the double integral. But we broke it into two pieces. So we said that dv dx is equal to, because remember the original equation was d squared v dx squared. So now we're saying dv dx, the slope, is equal to the first integral, and the deflection is equal to the second integral. Anybody else have any questions about that? Okay. So this is the general form, and because of the symmetry, it's actually valid anywhere on the beam. So that doesn't actually give me the maximum deflection, does it? I mean, unless I plug them in there. So what I can do is find the maximum deflection. And that's usually what most people go to the table for. So the general equation, due to symmetry, we can tell by observation that the maximum deflection will occur at the midspan, x equal to L over 2. If you don't believe that, then what you can do is take the first derivative of this equation and set it equal to 0. What is the first derivative of this equation? See, well, now we're going to go backwards. What is the first derivative of this equation? Is the slope. Go back here just a phase. This is our final answer, was the deformation is equal to this. Well, the first derivative of this is dv dx, which is the slope. So if you weren't sure where the maximum deflection is, you can take the first derivative of your expression for deflection, set that equal to 0, and where the slope is equal to 0 is going to be your maximum deflection. And I can draw that again. If the beam is deflected like so, doesn't have to be symmetrical, just if the beam's deflected at all like that, then wherever you have, oh, I botched that. Let's try that again. There, that's a little better. Wherever you have the slope equal to exactly 0, which is the first derivative of this equal to 0, you have found your point of maximum deformation. Okay, so in this case, I know the maximum deflection is going to be at L over 2. So I can simply plug L over 2 back into X here and here to get this, and then clean it up, and I get my maximum deflection V is equal to minus PL cubed over 48 EI. So this is V general, this is V max. And this right here is the value that you'll see when you look it up in a table, whether it's in this textbook or a structural theory textbook. Okay, I think that was the end. Yeah, that's the end of that one. So any questions at all on example 1? Okay. And this is a diagram, of course, showing that at L over 2, this is the maximum deflection that we're solving for here. Example number 2, find equations for beam deflection. Now we're going to take it up a notch. Now, instead of a point load, we have a uniform linear load. So I'll go through the same steps. I'm going to create a free body diagram. I've replaced my uniform load with a resultant point load of WL for the purposes only of finding my reactions. Finding my reactions, I have B is WL over 2, and A has to be WL over 2 as well. Decide on your cut points. Well, this one's clearly going to have one cut point because there's no discontinuities in the load at all. So one cut point completely describes this whole beam. So here's my free body diagram for cut 1. And I am going to, here's my end reaction, positive moment, positive shear. And so I sum my moments about 0.1. I have my end reaction times X. I have W pushing down times X. I'm sorry, times L over 2. I'm summing the forces, WL over 2 minus W times X minus V. That's my expression for shear. And here, more importantly, is my expression for moment, WL over 2 times X minus WX times X over 2 minus M. My moment is minus WX squared over 2 plus WLX over 2 is my expression for the moment, basically for the whole span from 0 to L. So far, so good? Okay, so now my generalized expression, dV dx EI is equal to the integral of the equation for moment. So I can plug in my equation for the moment right into here. Solve it, solve the integral. Minus x squared over 2 becomes minus x cubed over 6. WLX over 2 becomes WLX squared over 4 plus your constant of integration. Now, dV dx, the integral of which is VEI, so I need to take the integral of this result. So I just take this, plug it straight into here, and find my second integral. So minus WX cubed over 6 becomes minus x to the 4th over 24. WLX squared over 4 becomes WLX cubed over 12. C1 is C1x plus C2. Now, how do I solve for C1 and C2? I know you're all shy, but somebody shout it out. What am I looking for? Okay, thank you, Nick. I was beginning to wonder if my mic cut out. Boundary conditions. I solve for C1 and C2 using boundary conditions. So like the problem before, there's two things that I know. I know where the slope is equal to 0, and I know where the deflection is equal to 0. So I'm going to use those two pieces of information. Where the slope is equal to 0 will give me C1, where the deflection is equal to 0 will get me C2. So I solve the constants with my boundary conditions. The slope is equal to 0 at L over 2. Same as before. It's a symmetrical beam, so the point of 0 slope has to be at the midspan. So I take my expression for slope, and I plug in L over 2 for x, and I plug in 0 for dv dx, and I solve for C1. I cleaned it up a little bit. C1 is equal to minus WL cubed over 24. Now for the deflection, I have C1x plus C2. I can plug in what I know for C1 here. And then solve for C2. To solve for C2, I know that the deflection is always equal to 0 where my supports are. My support is at 0. So I can plug in 0 for all my x's, and I can plug in 0 for my deflection right here, and solve for C2. C2 is equal to 0. Therefore, my final expression is going to be wx to the 4th over 24, WLx cubed over 12 minus WL cubed x over 24. And so cleaning it up just marginally, this is my general expression, general equation for the deflection valid anywhere on the span. So you can look this up in the table. And it's a little messy, but this gives you, you plug in any value for x and it'll give you the value for your deflection. Now, due to symmetry, again, we know the maximum deflection is going to occur at the midspan, x equals L over 2. So I can just take my expression for deflection and plug in L over 2 for all my x's. And what I get is 1 over EI WL to the 4th over 384 plus WL to the 4th 96 plus minus WL to the 4th over 48. Take the, well, add your fractions basically. And what you end up with is minus 5 WL to the 4th over 384 EI. This again is what you'll find in your table. So we have derived a expression for a uniform load maximum deflection. For those of you who are going to go on to structural analysis and structural design, you will know this guy by heart after not too long. That this is a very common expression that you use all the time to check the deflection of simply supported beams. And again, that's where we're looking for that maximum deflection. Any questions on example number 2?
Professor Pratt,
Yes?
so what if you can go back a few slides, like maybe like 2 slides? I wanted to see something.
There.
Maybe like the last slide.
Uh-oh. Somehow okay. Sorry.
No worries.
Do.
Good recap.
Yeah, right. Okay, slow down a little bit here. Okay, in here somewhere?
Yeah, that looks fine. I was just making sure I saw that part. Okay, yeah, that's fine.
Okay.
I got it. All right.
And this should be posted on Blackboard too, so you can always go back.
Yeah, my bad.
Yeah. No problem. And also,
you.
I'm not uploading these to Blackboard anymore. Apparently, I ran out of memory. Each one of these is like a lot of memory. So I'm taking your suggestions and just uploading these to YouTube, and I'll just continue to do that to the end of the semester.
Can you email? Is that possible? The slides?
They're on Blackboard.
Okay. Well, I'm like, are we gonna still have lecture next week?
Yes.
Oh, okay. Okay, never mind.
Okay. I mean, hopefully I addressed that question. The slide presentation, the PowerPoint, is uploaded to Blackboard. You should be able to download that, no problem. It's just that the presentation that includes me talking and all of you asking questions. So the sound and the
Oh, okay.
presentation,
I
that's
get you.
yeah, that's the video. And the video is like 100 times bigger than the PowerPoint. So that's what's going to YouTube.
Okay, thank you.
Okay, no problem. All right, so example problem number 3, find equations for beam deflection for a uniformly loaded cantilever beam of L in length. So we're going to go through the first process here. We're going to create a free body diagram. The uniform load becomes a resultant for the purposes of solving for our reactions. We find our reactions. I sum my moments about the point, and I get a moment reaction of minus WL squared over 2. And I get a shear of WL. So now here's my problem. And I decide on my cut point. So I only need one cut point on the beam because it's continuous, no discontinuities. So for my cut point here, I'm summing moments about 0.1. I find my shear. More importantly, I sum my moments. So I have WL times X minus W times X over 2, plus I have this negative WL squared over 2 end reaction that I have to take into account, minus M, all equals 0. So M is equal to this expression. I have 3 terms. I have my end reaction. I have my end reaction in vertical. I have my end reaction moment, and I have the load as it is applied. So these 3 terms describe the moment as an equation anywhere on the span of X. So now we need to find our maximum deflection. Again, we go back to our basic equation. dV dx EI is the integral of m of x. So I plug in my 3 terms, m of x, and I find my integral. Okay, so you can see how each term is the integral of one of these terms, plus C1 is my constant of integration. Then I need to integrate again. So dV dx integrated is V, my deflection, is the integral of the resultant of the first integral. So all of this gets dumped into here, and I integrate again. So now I have, you can read, minus wx to the 4th over 24 plus wlx cubed over 6 minus wl squared x squared over 4 plus c1x plus c2. Now I need to solve for C1 and C2. What do I use to solve for C1 and C2? Making sure somebody's alive.
You do x at 0.
There we go. Slope at the fixed end, slope at 0, where slope is equal to 0. Yes, you're all correct. Absolutely. In a general sense, I was looking for, I solve C1 and C2 using boundary conditions. But you're absolutely right. That's the boundary condition I'm going to use. I know that the slope is equal to 0 at x equal to 0 because it's fixed. And I know that the deflection is equal to 0 when x equals 0 because it is fixed. The fixed fixes both aspects. Okay, so at dv dx, my slope is equal to 0 at x equal to 0. So I plug those in to this equation here. So dv dx is 0, and 0 goes in for each one of these x's here and here and here. Solve for c1. C1 is equal to 0. Now that c1 is equal to 0, this term drops out, and I have my VEI is equal to all of this plus C2. I need to solve for C2. Knowing that the deflection is equal to 0 at x equal to 0, I can plug those in. 0, 0, 0, 0. And so C2 also equals 0. Therefore, here's my expression. VEI minus WX to the fourth 24 plus WL x cubed over 6 plus WL squared x squared over 4. And this is the simplest form. So this is my general equation for the deflection, valid anywhere on the span. To find my maximum deflection at the far end from the fixed support, I know that my maximum deflection is going to occur at L. So I can plug in L into my general equation to find V max. And it comes down to minus WL to the fourth over 24 plus WL to the fourth over 6 minus WL to the fourth over 4. Combine your fractions, and your final answer is minus WL to the fourth over 8 EI. This will be the value that you see in a textbook. Any questions? Example 3. And that's what the deflected beam is going to look like. And you can see your maximum deflection occurs at L. Okay, are we ready? Example number 4. Example number 4 is similar, except for now this one is going to have an applied moment at the end of the beam. So we create our free body diagram, just like before. Find our reactions. MA is going to be equal to minus M naught, the applied load. The shear is equal to 0. Decide on a cut point. I only need 1. And create a free body diagram for cut number 1. Find shear and moment. My shear is equal to 0. My moment is equal to, there we are, minus M naught, or anywhere on the span between 0 and L. So that's a pretty simple moment expression. It's not even a function of x. So if I do dv dx, EI is equal to the integral m of x. That's equal to the integral minus m naught, which is equal to minus m naught x plus c1. I plug this into my second integral, and I get it minus m naught x squared over 2 plus c1x plus c2. How do I find c1 and c2, everybody? Somebody's going to say the magic words, where the slope is equal to 0, slope at 0. Yeah, boundary conditions. That's what I'm looking for, boundary conditions. Solve the constants of integration with boundary conditions. Okay, yeah, everybody knows. All right, so boundary conditions. dv dx is equal to 0 at x equal to 0 because it's fixed. So the 0 slope at the fixed end. So now I plug in 0 here, I plug in 0 here, I get C1 is equal to 0, which means plugging C1 equal to 0 here, this term drops out. So VEI is equal to minus m naught x squared over 2 plus C2. the deflection is equal to 0 at x equal to 0. Plug that in there, and C2 is equal to 0. Therefore, VEI minus m naught x squared over 2. So here is my general equation for deflection, 1 over EI minus m naught x squared over 2. Where is the maximum deflection going to occur on this beam? Well, again, it's going to be on the tip of the cantilever. So the maximum deflection will be the far end from the fixed support x equal to L. So I just plug L into x, and I get my Vmax as 1 over EI minus m naught L squared over 2. And I just simplified it. So this is the equation, again, that you'll find in your textbook. Any questions on example 4? That's what the deflected shape is going to look like.
I have a question.
Yes.
Wait, so why does the maximum deflection occur at like the open-ended side of the beam?
Uh-huh.
I was just wondering why. Make sure.
Well, I guess one answer is that this is the shape of the beam. Remember how I started it by saying sketch the shape of the beam? And that moment, as we applied that moment, produced a negative moment on the beam through the whole span. Here you have a negative moment. And so it produces a frowning shape. But it's fixed at the end, so it cannot have any slope at the end. So the frowning shape has to look like this. And so that's how you know that's going to be the maximum deflection.
Oh, okay. That makes more sense. Thank you.
Okay.
Got it.
Any other questions on this?
So for all of these general equations, they're the equations set up for that particular beam setup, right? So like the first one was a symmetrical beam. The next one was like symmetrical beam with a uniform distributed load. Next one would be a cantilever with a uniform load. We're just kind of like going down the list.
Yes, we did. Yes,
Okay.
we did. Yeah, absolutely. And I mean, these can get pretty darn complex. I mean, if you want to have some fun this Saturday night, try doing it with P located at L over 4. And it's absolutely totally doable. But what you have to do is take 2 cuts, and you have to find the integral of the, you have to find the equation of the moment from 0 to L over 4, and then a different equation for the moment from L over 4 to L. So 1/4 is one equation and 3/4 is the other equation. You need to integrate both of them and then add them all together. And it's absolutely totally solvable, but quite an exercise in calculus. So hopefully that helped answer your question in the sense that for these examples, I picked symmetrical or fixed end conditions. They are either symmetrical or they're fixed in. But this method absolutely applies to any beam, any loading condition, any beam at all. As long as you can get an expression in a function of x for the moment, then you can solve for these.
Okay, thank you. My next question, like a follow-up to that, would be like, so as you said, if we move it from L over 2 to L over 4, there was no like easy solution of, oh, the denominator moves or it becomes this much or anything. It's we have to solve from the beginning of, okay, now that we moved this point, this P to this L value, we have to start all over again.
Yes.
Okay.
Yes, exactly right. And the way that the, let's zip up there for a second. Let's look at that one. That's an interesting case. the textbooks and the manuals that will help you with these equations. Let's see, where are we? Example 2. Okay, example 1 right there. Okay, so say that was L over 4 instead of L over 2. The way that you'll find these equations, what they do is they solve this in terms of, they create a new variable where the distance from the end to the point load is A, and from the point load to B is B. So then A and B are actually variables. And then they'll solve this in terms of A and B. So your reaction at B is equal to a ratio of P times A over L. And the reaction at A is a ratio of P times B over L. So A and B go right into these two reactions, which then, when you sum your moments, you have a function of A built right into your moment here. And then you got to solve this, but think about this for a second. That's what it is. That's okay. So when we do these integrals, one thing that I left off, you know what? I'm glad you asked that, because one thing that I did inadvertently, that I simplified this, but each one of these integrals is actually, no, that was a horrible integral sign. Let's try that again. Okay. Each one of these is actually from some point to some point. Every one of these that I did for you was valid from 0 to L, or the whole moment diagram. So we were actually integrating from 0 to L, like so. So when you do that integral, the 0 term all drops out. But what happens if you needed to integrate from 0 to L, but you have two expressions? One is good from 0 to L over 4, and the other one is good from L over 4 to L. So you'd have one expression for moment here, and you'd have a different expression for moment here. And so you got to solve that. And so now you have all these terms, because you have all the terms you have in the first one. Half of them drop out because this is 0. But in the second one, they don't drop out. You have L over 4 for every x, and you have minus L for every x. So you have to add all this stuff together and then refine it all down to a final answer. And it was more than I was willing to take on for an example for this class. But it is absolutely and most certainly doable. Okay, did that last 5 minutes make everybody's head hurt, or did that help at all?
It helped. It answered my question, but yeah, it's a bit complex. I'm sure an example would help, but it gets the point across.
Okay, all right, well, the next lecture that we do, the very next lecture that we do, is we're going to use integrals to find deflections of beams through virtual work. And when we do that, you're going to see it is a bit more complex, but you're going to see exactly what I'm talking about, where you have to integrate part of the beam for one equation and the other part of the beam for another equation, and then add it all back together. I actually do have an example next time that does that sort of thing. So it's not exactly this, but this would be performed in a very similar manner.
Okay, thank you.
Okay, well, we have 7 minutes. Anybody want to talk about anything else for 7 minutes? Is there anything that I can tell you about the final in 7 minutes that would help you study over the weekend?
A question.
Yes.
So for the homework that's due Monday, homework 13.
Uh-huh.
So I think like the farthest it goes up to is chapter 9, stuff like that. So everything we're doing like today and like till like Monday. I mean, till like next Wednesday. That's gonna be on the final as well, right? Most likely.
Yes, it is.
Okay.
Yes, it is. But I do have to be cognizant. I do have to know that if it's material that I have presented that you have not done any homework on, then it would be a little unfair for me to ask you to do a full-blown problem for.
Yeah, that was
So
really what I was getting at with my question, though.
yes, yes, and you're absolutely right. You're absolutely right. So I can say that the material we're doing today, the material that we're doing next week, is potentially on the final. But I'm not going to ask you to do a whole bunch of calculations that you've had no practice on. So just because the flip side of that is that if you have not done any calculations on a problem, I'm not going to ask you to do something like what I just did here, for example, 1 through 4. But that doesn't mean that I can't ask you like fill in the blank type questions. Like if you're
Oh,
solving for beam deflection using the double integral method, how do you solve for C1 and C2? And your answer would be boundary conditions. And boom, you just got 2 good points.
oh, cool.
So,
Maybe
okay,
extra credit then.
no, that's part of the test. Well, what I'm
Okay.
saying is I can ask you questions on the test from the
Yeah.
material that we're covering in the last 2 weeks without actually asking you to do a full-blown problem.
Okay, I got it.
Okay, and
Thank
then
you.
Aiden and Juan, you are both asking the same thing. You're saying, oh my gosh, you're not going to ask me to do calculus on an exam, are you? No, I'm not going to ask you to do calculus on an exam other than fill in the blank. And when I say like fill in the blank, I would mean if you're going to find beam deflection using the double integral method, what is the general equation that you're going to use? And filling in the blank might be something like dv dx e times ei is equal to the integral of the function, or m as a function of x. That's not solving calculus, that's just regurgitating what the general equation is. Will we also continue to receive those extra handouts you had? You have them all. I gave you the 15th one. That was all that Giuseppe had created. So everybody now has all those handouts. And I will happily pass on to Giuseppe that they were well received if you guys like those. Perfect. Perfect. Great. Then I will continue to hand those out. Okay, so we're basically at the end of our lecture here. Today is Wednesday. That gives you some direction to study for over the weekend if you so choose. And then we still have 2 more lectures that I'm going to fill in a little bit more of the information as you need. Yes, I will put this on YouTube. Give me till tomorrow though, because I'm hungry for dinner. But yes, Ryan, I will definitely put this on YouTube. So with that, I will close out this meeting, and I hope everybody has a wonderful weekend. Thank you.